Welcome to VW 2.2. Today we're going to continue our study of complex numbers and we're going to get to do some pretty challenging examples here. So first, we'll start on our first one. Notice how the powers of I are quite high. So if you recall our table here, if you have I to the first power, that's simply I squared is -1, I cubed is -I, and I to the fourth is 1. So for problems like this is what you really have to have down in your head. And again, we can call this like powers of I. The key for you is you want to highlight this one right here. I to the fourth is 1, which means we're trying to generate multiples of 4 in there. So if I look at this first term, 4i27, I'm going to rewrite that as 4i to the 24th, and then times I to the third. So notice how this makes 27 here. And I do that because this thing, this I to the 24, because that's a multiple of this thing, I can just cross that out, and that becomes 1. So we're going to do that process for all of them. So plus 3, so think about 125. 124 would be the biggest power of 4 in there, or the multiple of 4, and that has 1 I left over. And 28 is nice because that's already good, so we can leave that alone. Next one we have 6 plus 2. So think about 53. The largest multiple of 4 in 53 would be 52. And then there'd be 1 left over, minus 5, and then I to the 80 times I. And again, if you're wondering how I made this thing 1, think of I to the 24th. You can think of it like this. I to the 4th to the 6th power. So that makes it more apparent. This is 1, and 1 to the 6th is still 1. So all of these I to the power multiple of 4, just cross them out, they're 1. Now we simplify. So I have 4, but notice how you have I cubed here? Look at your chart. I cubed is -I. So that's going to be -4i. Then we have plus 3i minus 2, all divided by 6 plus 2i minus 5i. So notice how the problem becomes significantly easier now. Let's rearrange it. -2 minus I over 6 minus 3i. We're going to multiply by the conjugate now to simplify. We'll continue our work here. So our numerator, we multiply this out, that's going to be -12 minus 12i plus 3. The bottom should be 36 plus 9. And that's going to become -9 minus 12i, all divided by 45. Now again, a lot of people want to stop here, but notice how it says a plus bi form. That means we have to separate it. So we separate and reduce. -1/5 minus 4 over 15i. So that's our first example. So in this next example, it says find the square roots of the complex number 21 minus 20i, and your answer should be in this form, a plus bi. So let's highlight a plus bi. That's the form we're working with. And notice how it says find the square roots. So what that means is that this number, 21 minus 20i, if you were to compare it to a plus bi, if a plus bi is a square root, that would mean if I square this thing, it should become 21 minus 20i. So let's keep going. Let's actually work this out algebraically. That's a squared plus 2abi, and that'll actually be a minus b squared because of the I squared. And now look at this thing. This might look like we can't do much with it, but we can actually do a technique and create a system here. So I call this technique equating components. Now what I mean by that is I'm going to highlight their real components here, so real numbers. So you have 21, a squared, and minus b squared. And we're going to make an equation out of that. I can say that a squared minus b squared has to equal 21. And now if I look at the imaginary components here, we have a negative 20i and a positive 2abi, which means negative 20i should equal 2abi. Now with this thing, there's not a lot we can do right now, so I'll leave that alone. But look at this equation. Let's reduce that. The i's can go away. I can divide everything by 2. So I get AB should equal negative 10. And now look at this. I have one equation here, another equation here. That's a system of equations. So now I can actually solve for a variable. I can say B should be negative 10 over A. And I can use that fact. So let's try to plug this in. So I know that A squared minus B squared is 21. So if I plug in the B I just found, A squared minus negative 10 over A squared should equal 21. Let's keep going. A squared minus 100 over A squared should equal 21. Let's multiply everything by the denominator. So now I have a to the fourth minus 100. That's equal to 21a squared. Now keep going. A to the fourth minus 21a squared minus 100 equal to 0. Now this is interesting because this kind of looks like a quadratic. Of course, there's a 4 here. So that just means when I factor it, we just have to write a squared instead of a regular a. So now factor 121. So think about factors of 100. You can do prime factor method or just think about it. I can see it's a 25 and a 4 here. And I know 25 should be negative because of that negative 21a squared. And look at that, we factored it. So I'm going to go up here. This would imply that a squared should equal negative 4, and a squared should equal 25. Now, even though we are working with complex numbers, I'm going to deny this one. This one doesn't make any sense because in the context of what we're working with, a plus bi, both a and b shouldn't be imaginary. These are actually just real numbers. This is the imaginary component right here, but we've taken out the I. So we're only looking for real number answers for a and b. So if a squared is 25, we root. The absolute value of a is 5, so a should be plus or minus 5. So now we have a. So that means there are two situations. A could be positive 5, so alright, if a is 5, or a could be negative 5, alright, if a is negative 5. So just plug in 5 right here. This is the equation that links a and b, or plug it in right here. Doesn't matter. So if a is 5, we're going to get b is negative 2. If a is negative 5, b should be positive 2. So now I'll put it back in the form I want. So a plus bi are two answers. So I write, therefore, our answers are going to be 5 minus 2i and negative 5 plus 2i. And there's our answers. Here's the last example. One of the roots of a quadratic with integral coefficients is 6 plus I root 5. Write the quadratic equation in the form ax squared plus bx plus c equals 0. So this is basically writing the equation from an answer. So the best technique we have is going to be reverse complete the square. And if it gives you 6 plus I root 5, if you want, you can rearrange that. Some books write it like this. If it looks better to you, just write 6 plus root 5i. So if this is an answer, then we know 6 minus root 5i must also be an answer. So to do reverse complete the square, I can just write x should equal 6 plus or minus root 5i. And let's just do the method. Subtract the 6, square, that's x squared minus 12x plus 36. That should equal -5. And look at that. There is our answer. So pretty much the same thing we did in our last chapter. Okay, so good luck on the homework questions and bring your questions to class.